Hi everyone. This is our first look at calorimetry. This is the style of calorimetry where we have to deal with molar enthalpy of solution. This is a situation where a chemical, some sort of solid chemical, is dissolved in the water that's in a calorimeter. And then the temperature of the water goes up or down. We have our regular setup for calorimetry. It's a transfer of energy. There's a heat gained and a heat lost. Don't forget that negative. We're going to say negative heat gained equals heat lost. That's really important for the math to work out. We have these two alternative situations. The water warms or the water cools. If the temperature of the water goes up, it was on the gain side. Okay. And the water just gets warmer. It's not going to boil or something like that. So it's just undergoing a temperature change, mc delta T for our water. The chemical is getting dissolved, and dissolving represents a type of enthalpy change. We're going to use NH. We should expect that the moles are not going to be straight up told to us because we're dissolving a solid. We should expect to have to do mass over molar mass for the moles of the chemical. And then we might get so then this M is the mass of the water, the specific heat capacity of the water, the temperature change of the water, all made negative equals the moles of the chemical multiplied by the molar enthalpy of solution. And we could be asked to solve for the mass of the water, the temperature change, even the initial or final temperature, the mass of the solute, or probably the most common one is to solve for that H, the molar enthalpy of solution. We have the exact opposite situation where the water could cool down. Notice it's the mirror image of the calculation, negative NH equals mc delta T. Here are the mc delta T's on the gain side. The temperature of the water went up. And this H is on the lost side. It was a negative H right there. A positive delta T, but a negative H. On the water cooling side, it's the opposite. That H is on the gain side. It's going to be a positive H. And here the water cooled down. The temperature of the water went down, a negative delta T. Two big themes to watch out for. Watch your units, especially if we're solving for the temperature change or the mass. Okay? But always we have to really be conscious of our units and really watch your pluses and minuses, especially this big one at the front. It's easy to forget that one or to lose track of it partway through a calculation. Here's an example. When 2.50 grams of lithium chloride are dissolved in 100 milliliters of water in a calorimeter, the temperature of the water increases by 6.80 degrees Celsius. Determine the molar enthalpy of solution for the lithium chloride. Okay, one of the challenges here is just identifying what kind of a question is it. Okay? It says calorimeter right in the question. That's an important signal. I would argue that a better signal is if we have numbers about two different things, then we're dealing with calorimetry. There's a chemical getting dissolved and some water. There's a chemical getting dissolved here, 2.50 grams of lithium chloride get dissolved. We have the mass of the lithium chloride. We have the volume of the water. We have the temperature change of the water. We have numbers about two different things. It's calorimetry. Here it does explicitly tell us the temperature of the water increases. That's obviously the water warms. So here we're going to start off with negative mc delta T equals NH. But what are we being asked? Determine the molar enthalpy of solution. It's saying, hey, let's find H. So I'm going to take that calculation over there and manipulate it. We're going to have H equals negative mc delta T divided by the moles, but I'm going to put mass over molar mass. Where the MC delta T is all about the water. The moles, the mass over the molar mass, was the chemical. Okay? So let's get to substituting. We have that big negative. This M is the mass of the water. And we had 100 milliliters, and 100 milliliters is 100 grams. The specific heat capacity of the water, the lowercase c, you might know it off the top of your head. You can find it in the data book. 4.19 joules per gram degree Celsius. And the temperature change, it's a positive value because we have increases by 6.80 degrees Celsius. This is divided by the mass over molar mass, which is the moles, which came from the chemical. Here it's the lithium chloride. We had 2.50 grams. We're going to divide by the molar mass of lithium chloride. Take your time. If you have to double check some values in the data booklet for the molar mass, perfectly acceptable. Lithium is 6.94, and chlorine is 35.45. The molar mass of lithium chloride is 42.39 grams per mole. My calculation is set up. There's a lot of buttons to push. Let's go for it. 100 times 4.19 times 6.8 divided by 2.5 over 42.39. What comes out on my screen is a really big number. It's negative 48,311.0352. We said, though, really watch your units. What's happening to our units here? Let's follow them along. Our grams cancel. Our degrees Celsius cancel. And that leaves us with joules in the numerator, and our grams cancel down there. We're actually ending up at joules per mole. That's a little bit surprising. We're accustomed to seeing our molar enthalpies in kilojoules per mole, but this one, it came out as in joules per mole. So now I have two choices. I could leave it in joules per mole and deal with my significant digits. Here I would have to use scientific notation. The three numbers in the question all have 3 significant digits. So my first option is to leave it in joules per mole, but put it in scientific notation. That's going to be negative 4.83 times 10 to the power of 4 joules per mole. That would be perfectly acceptable. There is a convention, though, that we often are going to express molar enthalpies in kilojoules per mole. So a second option is for me to do a unit conversion. I take my joules per mole and divide by 1,000. And now I'm at or negative 48.3 kilojoules. Either one of those would be perfectly acceptable. The question does not specify that it wants the answer in any particular units. Questions about molar enthalpy of solution, they're always when a chemical gets dissolved in water and then the temperature goes up or down. Because of those two opposite situations, we have two mirror image style calculations. Watch out for that big negative at the front. Overall, really watch your units. We saw that this one came out in a surprising way as joules per mole. We're always going to have the option to do a unit conversion if we want to avoid scientific notation, and I hope that helps.